Yeah, so first of all, I would like to thank the organizers for the invitation, and it's my great pleasure to be here. So today I'll talk about Legendrian, submanifolds, and the version of Arnold conjecture for them. So I'll talk about the homological Arnold chord conjecture and also some other related versions of this conjecture. But in order to do this, let me start with the basic definitions. First, let me start with the background. So we'll consider contact manifold, 2n plus 1 dimensional contact manifold. It's just an odd dimensional manifold, and it's equipped with maximally non-integrable hyperplane field. So what does it mean? It means that locally, at least locally, there is a one form alpha such that kernel of alpha is equal to psi, is equal to this vector hyperplane field, and alpha satisfies the property that alpha wedge the alpha to the nth power is different from 0. So as far as you have one such hyperplane field, you can define, and as far as you have one such form, you can define many forms, which gives you the same contact structure. You just multiply your contact form by nowhere vanishing function. Now, so this psi, I should say that it's called contact structure. And alpha is a contact form. Which defines now, if one fixes alpha, then to alpha we can associate some special vector field, which is called the Rib vector field. Victor already mentioned it yesterday, but let me say it once again. So we'll write it as R alpha, and it's determined by two conditions, namely alpha of R alpha is equal to 1, and the inner product of R alpha and D alpha is equal to 0. So again, this contact structure is given as a kernel of this one form. So the first condition simply means that this vector field is everywhere transverse to the contact structure. And if you think about the second condition, it simply says that the flow of this vector field of R alpha preserves contact structure. Then, given a contact manifold, we can consider some special type of submanifolds, so-called Legendrian submanifolds. So whenever we take n dimension, so whenever we have 2n plus 1 dimensional contact manifold, we consider n-dimensional submanifold. And we say that it's Legendrian, so lambda is Legendrian. If it's everywhere tangent to the contact structure. So for every x, Tx, lambda tangent space is a part of the contact structure. Now, what is a basic example of contact manifold? So we take standard Euclidean space, 2n plus 1 dimensional Euclidean space. And here we consider coordinates x sub 1, y sub 1, dot, 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 x sub n, y sub n, and z. And the so-called standard contact structure, which is defined as a kernel of the standard contact form, which is dz minus sum of yi dxi, I from 1 to n. So in this particular situation, Reeb vector field R alpha standard is just d over dz. It's not difficult to check. Now, of course, this example is, in a sense, canonical, because there is a theorem due to Darboux, which says that every contact manifold locally looks like a standard Euclidean space with this given contact structure. Now, let me say that you'll consider some special type of contact manifolds. Namely, first we start with a exact symplectic manifold, PD beta. And then we take its so-called contactization. So we take P cross R, then there is this Z coordinate on R, and we take a contact form dz plus beta. So it's a contactization of P d beta. So as you see in this situation, as in the case of the standard Euclidean space, the Reeb vector field is just d over dz. So let's say this is alpha, and R alpha is just d over dz. Then for this type of contact manifold, there is a special type of projection called Lagrangian projection. We denote it by pi sub L, and it's just a map from P cross R to P. So it's just a standard projection. So let's say we have xz, and we map it to x. Now, why it's called Lagrangian projection? Because, so let's assume, there I just gave a standard definition of a Legendrian submanifold, but let's assume that all our Legendrian submanifolds are closed. So we'll assume that all lambdas that we consider are closed. Lambdas that we consider are closed, and let's say oriented and connected. So as far as we have these assumptions, and we take lambda in P cross R, it's Lagrangian projection generically. Generically is an immersed exact Lagrangian submanifold of P d beta with a finite number of double points. So again, we know that Rib vector field in this situation is just d over dz. So double points of this projection are, of course, in one-to-one correspondence with the trajectories of Rib vector field R alpha, again, it's just d over dz, which start and end on lambda. Okay? So it comes only from the definition of this Lagrangian projection, so it's easy to see. And let's denote the set of such, so the set of such trajectories will be denoted by Q of lambda. So as I said, generically, the size of this set is finite. Now, the topic of Arnold chord conjecture is exactly the size of this set. So the first question is it non-empty? And we know by Gromov's theorem, if you assume non-displaceability of a Lagrangian projection, that there is at least one element in this set, if you consider if p is equal to r to the 2n plus 1. So that's what we know by Gromov's theorem. So Gromov in these settings tells us, let me be safe and say that p is equal to r to the 2n plus 1, and n is greater than 1, that the size of the set is at least 1. The question is, can we do better? Can we get better bounds? And this is exactly the topic of the conjecture, as I already said. So the conjecture due to Arnold. And here I have to mention something. So actually, in this form, it was never formulated by Arnold. So when my collaborator, Yorgos Dimitroglou, Rizal, and I started thinking about this conjecture, we tried to find the actual reference. And unfortunately, we didn't find it. So some people will call it Arnold type conjecture, but I'll write just Arnold. So it says the following. So let's assume that we have a Legendrian submanifold lambda living in P cross R with a contact form dz plus beta. So again, it's Legendrian. Besides that, the Lagrangian projection of this Legendrian is Hamiltonian displaceable. Then the number of this double points, or the number of trajectories, is greater or equal than 1/2 sum of Betti numbers of lambda. And when I write Betti numbers, let me be safe and say, for example, over Z2. Okay. Sorry? Lambda is compact, so we assumed here all lambdas are closed. Yeah, so if you don't make this assumption about closeness, if you don't consider compact Legendrian, then it's possible to have infinite number of double points. But for, yeah, okay. But you are absolutely right. It's a good question. Okay, let me try to be brave and use this machine. Okay, works. Great. So now the question is, do we know that this? Do we know any examples when this conjecture doesn't hold? So examples when Arnold conjecture doesn't hold. As it turns out, there are some. And they are quite recent ones. So first, I should mention that there was a work of Sauvaget It appeared in 2004. And Sauvaget constructed by hand some example in R5 where the conjecture is wrong. This work, I should say, wasn't really noticed. So it became famous, or at least known later, when Amy Murphy discovered so-called loose Legendrian submanifolds. And then people realized that the example of Sauvaget is a loose example. So as I mentioned, Amy Murphy, in 2012, this was her PhD dissertation. Proves that for certain Legendrian submanifolds, so-called loose Legendrian submanifolds, so she proves that so-called loose Legendrian submanifolds satisfy an H principle, which means that there is no way to get the rigidity of this type for these submanifolds. So, you know, in contact and symplectic topologies, there are usually two sides. There is a rigid side and there is a flexible side. So Arnold conjecture belongs to the rigid side. There is also a flexible side. And this topic becomes quite hot these days. There are many people working on this. And so this loose Legendrian submanifolds, they belong to the flexible side. So I think it's useful, let me say what these submanifolds are. So first of all, they exist. These Legendrian submanifolds exist in the, let's say, Euclidean space, only starting from dimension 5. So in dimension 3, there are no such submanifolds which satisfy H principle. Okay, so And again, I should say that here we take a standard contact form. So we say that lambda is called loose in R to the 2n plus 1. And here I will write this form in a slightly non-standard way. So I need to have two preferred coordinates, x and y. So minus y dx minus sum I from 1 to, let's say, n minus 1, yi dxi. If there exists a neighborhood let me write U in R to the 2n plus 1 such that in U, let me write this way. We have the following picture, the following situation. So to be more precise, I should say that there is a neighborhood which is contactomorphic to a certain neighborhood, but let me write it down this way. It doesn't really matter. And let's assume that basically this neighborhood lives with this coordinate, so we actually have these coordinates. Otherwise, I should say that we have some neighborhood which is contactomorphic to the neighborhood with these coordinates where we have some structure. Okay, so with the following situation, I'll write it down, ABC and capital lambda sub 0. So this R ABC is a set of x, y, x sub 1, y sub 1, x sub n minus 1, y sub n minus 1, z, such that x and y are smaller or equal than 1, then the norm of x sub 1, x sub n minus 1 is smaller or equal than b. The norm of y sub 1, y sub n minus 1 is greater or equal than c, and z is smaller or equal than a, where b times c is greater or equal than a, and lambda sub 0, this capital lambda sub 0, is a part of your lambda that you see in this neighborhood U, and it looks in the following way. So lambda sub 0 is a product. So let me write, is a product of some q times small lambda sub 0, where q is a set of x sub 1, y sub 1, x sub n minus 1, y sub n minus 1, said that y sub 1 is equal to dot 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 is equal to y sub n minus 1 is equal to 0. Then the norm of x sub 1, x sub n minus 1 is smaller or equal than b. And this small lambda sub 0 is Legendrian in let me write R3. It's actually a box, but let me write R3. So again, we have dz minus y dx. So defined by the following diagram. So we take only x and z coordinates. Here we have x, here we have z. So we remember that x is from -1 to 1, z is from -a to a. And here you have something which looks like a fishtail. So this type of projection to x, z coordinate, let's say in r to the 2n plus 1, or in general, you can define it also in the one-jet spaces. So this x, z projection is usually called front projection. So again, Legendrian is called loose if you can find a neighborhood so that in this neighborhood, Legendrian looks like a product of Q with a curve which looks like a fishtail in this Lagrangian projection. So as far as you can find a small piece of Legendrian with this type of behavior, you know that Legendrian is loose, and such Legendrian satisfy each principle. So for these Legendrians, let's say all the Floer type invariants vanish. So you can think about it as a virus. As far as you can find this virus or some bad part in DNA, it destroys everything. It destroys all the homological and all the pseudo-holomorphic invariants. So now, yes?
What's the origin of this conjecture, Arnold conjecture? Why one Alfred, for example?
Well, you see that when you have a Legendrian manifold, again, in the Lagrangian projection, we have inverse Lagrangian. So somehow, I think, again, so I didn't find this type of formulation in the literature, but I think it's related to the Arnold conjecture for Lagrangians. And since you have inverse Lagrangian in this case, I think I don't want to speculate. I don't want to speculate too much. I have some reasons coming from the Floer theoretic side, but to understand why it was formulated this way, I don't really know, to be honest. And again, so I didn't find this type of formulation anywhere. But as it turns out, it appears to be true in many cases. So. With exactly this lower bound, and sometimes you can prove even better bound. So sometimes you can formulate a so-called whatever. So there is no strong Arnold conjecture in this situation or whatever. So something that we canonically call strong Arnold conjecture, but sometimes you can even prove a better bound, which can be seen as a strong Arnold type conjecture.
Okay, and in this case, I mean, you got to have at least one self-intersection, and you can have just one.
Yes, you can have just one. Yes, exactly, it's true. So there were some works about this. So there is a work, for example, of Murphy, Eliashberg, Ekholm, and Smith. Yeah, where they get this type of construction. Okay. Okay. Now, and actually, the first such formulation appeared in the work of Ekholm, Etnayer, and Sullivan, when where they defined a Legendrian contact homology for Legendrians living in R to the 2n+1. So, and they called it Arnold conjecture. So he just followed the words. Right, so then the question is, we have some examples when this conjecture doesn't hold. The question is, what do we know? I mean, maybe it doesn't hold at all. Maybe this formulation is wrong. And as it turns out that it holds for a big number of examples. So, when this conjecture holds, first, there is a result of Ekholm, Etnayer, Sullivan, and also Ekholm, Etnayer, and Sablov. So for the first result, I should write 2005. I think for the second one, it's 2007. These two groups of people prove that actually, maybe let me write it down as a conjecture. So AC will be the short name for this conjecture. So Arnold, so homological Arnold conjecture. So they prove that AC holds for Legendrian submanifolds of R to the 2n+1 with a standard contact structure, provided that, now I'll write some words. Later I'll explain what they mean. So provided that the Chekhanov Eliashberg algebra A lambda admits an augmentation. So let me say why there are two groups of people. So in fact, this type of proof, so the proof of this conjecture, appeared in two different papers. The methods used for the proof were slightly different. So for those who know what is a duality along exact sequence in Legendrian contact homology, it was proven with a duality along exact sequence in the second case. And also the conjecture as I formulated it, again, so it says that the size of this set of trajectories is greater or equal than 1/2 sum of Betti numbers. Right? Was proven in 2005, but there is a graded refinement of it. And this graded refinement was proven in 2007, where you actually you have some gradient associated to these trajectories, and you can say how many, you can write some bounds for the number of trajectories in a given gradient component. Okay. So now, later I'll explain what the Chekhanov-Eliashberg algebra is, and what is this augmentation, and what does it mean if we have such augmentation, at least in which situation we have this type of augmentation. Also, one can prove some algebraic refinement of this result. In fact, it's just algebraic refinement. So if you ask algebraists, algebraists will say that the proof looks very similar, or at least, or even the same algebraically. So one can write algebraic refinement, and so again, we can say that AC holds. Then we have the same type of sentence up to Chekhanov-Eliashberg algebra. So provided that the Chekhanov-Eliashberg algebra, and I'll write A lambda to make it easily readable. So A lambda admits a k-dimensional linear representation for k greater or equals than 1. So as I already mentioned, I'll explain the meaning of Chekhanov-Eliashberg algebra and of augmentation, but roughly speaking, you should think about augmentation as a one-dimensional representation. So the way to improve it and why it's algebraic improvement, because you go from one-dimensional representation to representation of any dimension. Okay. Now, okay, you can say, well, is it actually useful? Do you know any examples which satisfy the first condition but doesn't, which satisfies the second condition but do not satisfy the first condition? And as it turns out, there are such examples in all dimensions. Okay. So as you see, this type of improvement is an improvement of the original theorem due to Coleman, Nair, and Sullivan. When we have the same type of condition, when we have a slightly weaker condition, but we get the same type of inequality. Now, there is a different strategy. Sometimes, if you make stronger assumptions, you get better inequality. And so let me write it as theorem 1. And also, there is a theorem 2. I'll write it down. Again, there will be some strange terms in it, but later I'll explain what they mean, and I'll explain how to prove it. Okay? So, and it's again Yorgos Dimitroglou-Rizal. So, we would like to make some stronger assumptions. So what are they? The stronger assumption is the following. So we assume that, so let lambda be a Legendrian submanifold of R to the 2n plus 1, let's say standard context structure. And I didn't mention it along the talk, but again, so first I wrote P cross R, and then I switched to R to the 2n plus 1. Whatever I mentioned works in P cross R as well. But I mean, for the proof, and actually for examples that we can build only in Euclidean space, I'll stick with R to the 2n plus 1. So again, so we have Legendrian living in R to the 2n plus 1 with a standard context structure, such that there exists an exact Lagrangian filling and I'll write it down as L lambda of lambda. Then so let me write some extra words. Assuming some good properties of this filling. Of this filling L lambda, and by good I mean Maslov 0 and spin. The following inequality holds. So the size of this set is bounded from below by by a stable Morse number of this L lambda. And moreover, if L lambda does not satisfy good conditions, then the size of the set is bounded from below by the following quantity. It will be slightly difficult to write. So sum of beta i's of L lambda, where i's from 1 to n, from 2 to n. Actually, let me write i's. Okay, I is different from 1. Let me write this way. Plus 2 plus d of g, where G is a finite simple or solvable epimorphic image of pi 1 of L lambda. D is a, so D corresponds to the minimal number of generators. Minimal number of generators of this group. And also, so we need to, so provided that, we need to make one extra assumption, provided that pi 1 of L lambda is perfect. Okay, so whatever I've written looks slightly complicated. But the point is, you have Legendrian lambda, and we make an assumption that this Legendrian admits so-called exact Lagrangian filling. I'll explain what it is. Then, if this filling is good, you have this type of inequality. So the number of these trajectories is bounded from below by the stable Morse number of this filling. So again, I'll provide the definition, but roughly speaking, it means that it's a minimal number of critical points on this manifold of the Morse functions on this manifold if you stabilize it by the product with the standard Euclidean space and the dimension of this Euclidean space vary. And if you don't have these good conditions, then you have another inequality, which looks complicated. But there are some reasons why it looks complicated. So first of all, we have sum of Betti numbers, where I is different from 1. Then we have 2. Actually, I wrote that the fundamental group must be perfect. So if you don't have this perfectness, you don't have this 2. Then we have D of G, where G is an epimorphic image of the fundamental group, and D corresponds to the minimal number of generators. Okay, so again, so perfect group is just a group with the properties that that it doesn't have non-trivial abelian quotients. I can write it down. I mean, or whatever I'll say. And solvable means that there is a normal series with the property that each factor in the series is abelian. Okay, so let's not use a complicated group theory here, but. Yes, here I don't have 1/2, but you see there I have beta numbers of lambda of a Legendrian. Here I'm talking about the beta numbers of the filen. Okay, but what I'm saying is that this type of inequality is typically much stronger than the homological Arnold chord conjecture. Okay, now I'll spend some time explaining all these terms. So again, this is theorem 1, theorem 2. I'll talk about them. So if you don't understand the terms, don't worry, I'll explain what they are. Okay.
Which condition Murphy's example does not satisfy?
Okay.
This is not contradict with Murphy's example, I think. So, for which condition her example does not satisfy?
You mean, are you talking about theorem 1? This one?
So, does not satisfy the condition.
You mean, do I know any examples with a... Okay, so you see it's possible to have Legendrians with many filens, right? So here I'm talking about some particular filen. I can cook up examples of filens with a Maslov different from 0. I can do it. So I won't write it down at this point, but if you ask me, if you put me in the room and give me a chalk, I'll do it. Okay. But so there are some examples. So this condition is non-empty. Okay. Okay. So let me start explaining all these words. And also, I should mention that in the name of my talk, there are Lagrangian cobordisms. So here, I didn't say cobordism anywhere. But you should understand that filens are cobordisms. These are some special cobordisms. Okay, so first let me start with the Chekhanov-Eliashberg algebra. And I should mention the following. So there are two. So Chekhanov-Eliashberg algebra is an invariant of a Legendrian submanifold. So first it was introduced by Chekhanov. And it was defined originally only for Legendrian knots in three-dimensional Euclidean space. And the invariant of Chekhanov, so this algebra, was defined completely combinatorially. Then Eliashberg, Giventhal, and Hofer came with the idea of the symplectic field theory. And as it turns out, this Chekhanov's algebra fits well in this theory. So there is a reformulation of this algebra, even in three-dimensional situation, using pseudo-holomorphic curves technique, right, using pseudo-holomorphic curves. And also, I think the equivalence of two definitions in dimension 3 was proven by Lenny M. So what I'll write down will be a SFT type, so symplectic field theory type definition, because I'm trying to work in all dimensions, and I don't want to consider only the combinatorial version. So again, we have lambda. To this lambda, we associate this set Q lambda. And I should also say probably that the elements of the set, I mean, I said trajectories all the time, but people also use name rib chords. So from now on, I'll say rib chords. Okay, so the elements of this set are rib chords. And Chukhanov-Eliashberg algebra, we denoted by A lambda, is just a unital, non-commutative algebra. Okay, let me be slightly lazy and write over Z2. You can write it down over more complicated coefficients. So you can write it down over Z H1, let's say, lambda, or even more than that. But we will consider only Z2 version. So over Z2, freely generated by the elements of this set, Q lambda. Again, so generically, we know that this set is finite, and we will assume, so I should also say this, so we assume that we are in the generic situation. So we are always in the generic situation. Generic situation, meaning that this set is finite. Okay. So again, it's unital non-commutative algebra. If you have at least one element of Q lambda and it's non-commutative, you can imagine that it's infinite dimensional. Okay? And in the theorems, you mean in which one? So intersections to be, but it's a, yeah. So it's, you mean for rib chords for the projection, but it's a genericity condition. So by genericity, you know that you only have finite number of transverse double points. Yes, yes. So it's a genericity condition. Thanks. So right. So we have this algebra. Let's say over Z2. There is certain gradient, and I'm really glad that Victor mentioned Conley-Zender index. So at this point, I won't explain what it is. It's better if I explain how differential looks like. But there is a gradient coming from Conley-Zender index. So there is a gradient. So coming from Conley-Zender index. But I think it's much better if I explain how differential looks like. So what is this differential? How to define it? So first of all, you take r to the 2n plus 1, right? Our contact manifold. And you take a product with one extra r. And here, you take a symplectic form, d of e to the t, alpha standard. So this type of symplectic manifold is called symplectization. Of r to the 2n plus 1 alpha standard. And here we consider some class of almost complex structures. So we consider, let me write, admissible almost complex structures. I'll explain what it means in a second. So again, almost complex structure is just an endomorphism of the tangent bundle with the property that its square is minus identity. Why it's different from the complex structure? Because, I mean, in general, because you don't have local coordinates where you can write it down in a good way. Now, so this admissibility simply means that so this J's, so almost complex structure J's, and this admissibility simply means that we map contact structure to itself, and we want this J to be so, and J is R invariant, and by R I mean this T direction. Okay, so I have to say that, sorry, I forgot to say. So this T in this formula, right, it comes from this extra factor. And here we have J invariant, and this is a J invariant with respect to this T direction. And also we have d alpha standard of VJV is greater than 0. This is for V in the contact structure. And finally, we want to map G of d over dt to d over dz to our vector field. Now, so again, so we have a simplification, and we have this class of almost complex structures, and now we consider the following maps. So we define the following modular space of maps. So we consider maps F, looking as AF, let's say from D2 minus X y sub 1 y sub k, DD2 minus X y sub 1 y sub k, and we map them to R to the 2n plus 1, and here we have a d of ET alpha standard. On this part, so we can consider it as living in C with a standard complex structure I. On this part, we have almost complex structure J. And now I'll write some conditions. I'll try to be precise. So again, this A corresponds to the R factor, and F corresponds to the R to the 2n plus 1. So we also assume that so C plus and let's say C1 minus, CK minus are rib chords of length T plus T T1 minus T K minus respectively. Okay, and now with this information we consider the following conditions. So A of P goes to infinity when P approaches X, and A of P goes to minus infinity when P approaches yi. And now let's take this point X, right? So this point X, again, it lives on the boundary of this disk. And we consider polar coordinates near it. And we want to have that limit of, so here we have coordinates rho and theta. Limit of f of rho ei theta whenever rho goes to 0 is just a c plus of minus t plus theta over pi. And again, so whenever we have yi, we also consider polar coordinates. And in these polar coordinates, limit as rho goes to 0 of f rho ei theta is equal to ci minus t I minus theta over pi. Okay, so there are some conditions. It's much easier, of course, to write it down in terms of picture, to present it in terms of picture, but I think it's a good idea also to write down the precise formulas. So in terms of picture, it means the following. So you have a disk, and you remove some points from the boundary, x, y sub 1, y sub k. And again, we can assume that it lives in Ci. Yeah, I forgot to say that this, okay, so this F's must be, so F is ij holomorphic, of course. Before I draw this picture, holomorphic. Okay, so of course we want holomorphic, to consider only holomorphic maps. And in terms of picture, how does it look like? Here I also forgot something, sorry. I have to write down also R times lambda. Now it's complete. So again, disk is going to the product, but the boundary goes to the cylinder over lambda. Okay, so again, here we have lambda. Here we have cylinder. Here we have C plus, C1 minus, C2 minus, CK minus. Okay, and this is T. Okay, again, so we consider disks with one positive asymptotics at C plus, at infinity, and many negative punctures, which are asymptotic to C1 minus, CK minus, to the ripcords at negative infinity. And the boundary of this disk lives on the cylinder over Legendrian lambda, okay? Where when you take this R, of course, I mean this R corresponds to the T coordinate, okay? As I draw it here. Let me just write the formula of differential, and then I'll stop. Okay, so okay, so the moduli space of such maps will be denoted by mj c plus, c1 minus, ck minus. And d of c plus is defined to be a sum with respect to c1 minus, ck minus. And we want the dimension of the moduli space of such disks when we quotient it out by R, right? And what is this R? This R corresponds to the shifting in this T direction. So whenever you have disk like that, you can always shift it in T direction. So we want to assume that the dimension is 0. Also, there is a compactness theorem which tells you that you get a 0-dimensional compact manifold, which means finite number of points, and then you can count them. So basically, we have number of elements in MJ of C plus, C1 minus, CK minus, R, C1 minus, CK minus. And the homology, let me write one more thing. So the homology of this A lambda D is so-called Legendrian compact homology of lambda, and by theorem of Ecole, McNair and Sullivan, this homology is a Legendrian invariant. So d square is equal to 0, and the homology of A lambda D is a Legendrian invariant. I think this is a good point to stop. Again, so far I just defined this algebra. As you see, this algebra is huge infinite dimensional, which means, I mean, Victor says that sometimes it's useful. It's true that sometimes it's useful, but it's usually difficult to deal with. So usually, in order to deal with this algebra, we need to linearize it in some way. And that's the point why we need augmentations. These augmentations are just linearizations of this algebra. Okay, so next time I'll continue from this point. Thank you very much for your attention.